recollect that extrinsic semiconductors are of two types. P-type semiconductors, in which the doping agents are the trivalent impurities, and in which the majority charge carriers are holes. And N-type semiconductors, in which the doping agents are the pentavalent impurities, and in which the majority charge carriers are electrons. Consider a p-type semiconductor crystal, to which a specific amount of a pentavalent impurity is added in high concentration. This creates a semiconductor crystal that contains both a p region and an n region. The boundary that separates the p region in the semiconductor from the n region is called the p-n junction. It is important to note that a p-n junction cannot be formed by joining two separate pieces of p-type and n-type semiconductors. Because of the surface irregularities of the two different crystals, and because such continuous contact at an atomic level is not possible. If such a junction is formed, the junction would not be continuous and would therefore inhibit the flow of the charge carriers. Now, let us again look at the semiconductor crystal that contains both the p and n regions separated by the p-n junction. We know that in the p region, there is a higher concentration of holes, and in the n region, there is only a smaller concentration of holes. Similarly, in the n region, there is a higher concentration of electrons, and in the p region, there is a smaller concentration of electrons. This causes the holes to diffuse from the p region to the n region across the p-n junction. Physically, this means that some of the valence electrons just to the right of the junction may fill the vacancies just to the left to the junction. Simultaneously, the conduction electrons also diffuses from the n region to the p region across the p-n junction. The ions do not move because of their heavy masses. This diffusion of the majority charge carriers across the p-n junction creates a diffusion current that is directed from the p region towards the n region of the semiconductor. When electrons diffuse from the n region to the p region, they leave behind stationary, positively charged atoms of the donor impurity. Similarly, when holes diffuse from the p region to the n region, they leave behind stationary, negatively charged atoms of the acceptor impurity. This creates a layer of negatively charged ions towards the p side of the p-n junction, and a layer of positively charged ions towards the n side of the p-n junction. The layer of stationary negative charges towards the p side of the junction opposes the diffusion of electrons from the n side. Similarly, the layer of stationary positive charges towards the n side of the junction opposes the diffusion of holes from the p side. This creates an electric field near the junction, which is directed from the n side to the p side. Thus, a small region is created on either side of the p-n junction where no free charge carriers can exist. The region free of moving charge carriers extends on either side of a p-n junction and is called the depletion region. The separation of charges in the depletion region creates a potential difference that opposes the diffusion of electrons in the n region and holes in the p region across the p-n junction. The electrons and holes have to overcome this potential difference, called the barrier potential, to freely diffuse across the p-n junction. The potential difference across the depletion region gives rise to an electric field directed from the layer of positive charges towards the layer of negative charges. The electric field across the depletion region causes electrons in the p region to move to the n region. This is called the electron drift. Simultaneously, the electric field across the depletion region causes the holes in the n region to move to the p region. This is called the hole drift. This drift of minority charge carriers across the p-n junction creates a drift current that is directed from the n region towards the p region of the semiconductor. Thus, we observe that the diffusion current and the drift current across a p-n junction are opposite in direction. We have to remember that at the time of formation of the p-n junction, there is no depletion region. Thus, there is a high diffusion current but no drift current. As the depletion region gets formed, the diffusion current decreases and the drift current increases. In steady state, the diffusion current and drift current become equal in magnitude and there is no transfer of charge at any cross-section. Thus, a crystal with p-n junction in an isolated state is electrically neutral. A p-n junction with metallic contacts provided at its ends forms a basic semiconductor device called a diode. A diode is represented by the symbol shown here. Semiconductor diodes are the fundamental components of most of the electronic gadgets we use in our daily lives. We have learned